Hello everyone, and welcome back to another explainer. So I want you to just stop and think for a second. Right now, literally billions of dollars, highly sensitive medical records, state secrets, your personal messages, they are all floating through the air, protected by absolutely nothing but math. It's kind of wild when you actually pause to think about it. I am absolutely thrilled to guide you through today's topic because we're looking at the invisible, incredibly complex, and frankly, shockingly fragile mathematical foundation that protects our entire digital lives. Every single text message you send, every bank transfer you make, every private search you conduct, it literally all relies on modern cryptography. But that begs a massive question. How safe is that math, really?
I mean, can a single line of code actually break perfect security? It sounds like a dramatic movie plot, right? Like some hacker in a dark room typing furiously. But in the world of modern cryptography, it's not Hollywood. It's a terrifying reality. Today, we're going to pull back the curtain and uncover the extreme, almost unbelievable brittleness of the security systems we implicitly trust every single day.
Okay, let's dive right into this. First, we'll outline the modern cryptography foundation. Second, we'll visit the ghosts of Ciphers past. Third, we'll uncover the extreme brittleness of crypto systems. Fourth, we'll explain the wild world of side-channel attacks. And finally, number 5, we'll wrap up with the ultimate rule: why you should never, ever roll your own crypto.
Starting us off with Section 1, the Modern Cryptography Foundation, and how it's designed to protect data absolutely everywhere. So, modern cryptography essentially has two primary functional roles, and they are both completely indispensable. First, we have data protection. Now, on the slide, you'll see a vault icon, and that represents data at rest. Basically, this means protecting your files when they're just sitting there, on your physical hard drive, your phone, or locked away in some massive cloud server farm. The other half of this is data in motion, which is represented here by the secure transit tunnel. This ensures that when your data is actively traveling across public networks, like when you hit send on an email, any intercepted packets are completely unreadable gibberish to eavesdroppers. The second major role is protocol integration. You'll see the icon labeled TLS integration. This is absolutely crucial. Standard protocols, most notably Transport Layer Security, or TLS, rely on cryptography to actually function. TLS is exactly what puts the S in HTTPS at the top of your web browser. This kind of standardization is vital. Think about it. Without standardized integration, everyday software developers would have to invent their own complex mathematical encryption for every single app they build, and honestly, that would be an absolute security disaster. Instead, standard protocols allow developers to easily plug in overwhelmingly strong, pre-built encryption. Moving right along to Section 2, Ghosts of Ciphers Past. Let's see how we transition from relying on basic human intuition to requiring absolute mathematical proof. Historically, encryption was treated almost like an art project. It relied heavily on casual design. You know, if a system intuitively looked confusing or just felt secure to whoever created it, they went ahead and deployed it. It was essentially a game of cleverness between generals and spies. But modern cryptography? It doesn't care about your intuition at all. It strictly requires defining precise, formal security goals up front. Today, to even attempt to argue that a system is secure, researchers have to provide rigorous, mathematical constructions, and those constructions must meet those specific goals under heavily scrutinized, highly plausible mathematical assumptions. We completely shifted from building clever little puzzles to requiring definitive, hardcore mathematical proofs. If we look at those early historical ciphers, they relied on incredibly simple tricks. Take the substitution shift method listed here. This is exactly what it sounds like. You simply shift the alphabet over a few spots, so an A becomes a D and a B becomes an E. Or consider the other common method, transposition, where you just scramble or permute the order of the letters. These methods were entirely casually designed. And sure, while they might have successfully baffled ancient armies a few thousand years ago, modern cryptanalysis can break them in literally fractions of a second, using basic frequency analysis. But, and this brilliantly illustrates a key point in our story, there is one massive exception in history. It proves that perfect security isn't just a theoretical myth. It's called the one-time pad, invented by Gilbert Vernem back in 1917. This is a highly pivotal, legendary historic cipher because, unlike those simple substitution ciphers we just talked about, the one-time pad actually provides mathematically perfect security. If you use it exactly correctly, it is theoretically impossible to crack. Period. It doesn't matter if an attacker has 1,000,000 supercomputers running for 1,000 years. They cannot break it. However, as with most things that sound too good to be true,
This mathematical perfection comes with a massive, highly impractical catch. First, the key used to encrypt the message must be truly mathematically random. It cannot just be generated by a predictable computer algorithm. Second, and this is the real kicker, the key must be exactly as long as the message itself. Let's just put that into perspective for a second. Think about what that actually means in today's digital world. If you want to securely stream a 2 GB high-definition movie, you would need to securely, physically pre-exchange a truly random 2 GB key with the server before you could even hit play. If you literally have to securely hand-deliver a massive random key to a server just to watch a movie, well, that encryption is essentially useless for modern high-speed, high-volume internet communication.
And you can probably guess what happens when people try to cheat those strict rules. When historic methods tried to cut corners, they failed catastrophically. Take the so-called two-time pad. Let's say you get lazy and you reuse a one-time pad key just once to send a second message. Boom! You've just given the attacker everything they need. By simply overlapping those two intercepted messages, the attacker can use straightforward mathematical deduction to cancel out the key entirely, leaving them reading both of your secret messages in plain text. A perfectly secure system is instantly destroyed by one lazy decision. Then you have simple linear congruential generators. These are basic algorithms used to create long strings of numbers that look completely random to the human eye. They provide that dangerous, intuitive security we talked about earlier. It looks like random gibberish, so it must be safe, right? Wrong. Mathematically speaking, they are incredibly predictable and easily bypassed by formal attacks. And that harsh reality perfectly sets up Section 3, the brittleness of crypto systems, and what is known as the single error rule.
This brings us to what is perhaps the most critical lesson of this entire explainer, the single error rule. Modern cryptography is fundamentally, brutally unforgiving. You can have a mathematical model that has been reviewed and proven to be perfectly secure by the world's absolute greatest minds. But that perfectly secure model can be rendered completely and utterly insecure by just a single, microscopic error in its specification or in the actual computer programming used to implement it. It is an incredibly, terrifyingly brittle ecosystem.
And because of this extreme brittleness, we run into a terrifying software engineering paradox when it comes to testing. In standard software testing, if you run a unit test and your code successfully encrypts a file, and then it successfully decrypts that file back to its original readable state, the test passes. The code functions perfectly. High fives all around. But the cryptographic reality is totally, wildly different. A crypto system can function absolutely perfectly for the user, encrypting and decrypting data smoothly. No crashes, no errors, while simultaneously possessing a hidden flaw that leaves it wide open to an attacker. Standard software testing is practically useless for proving true security. Why? Because normal tests look for functionality. They check if the machine turns on. Attackers, on the other hand, look for bizarre edge cases and hidden, microscopic vulnerabilities in the shadows that standard tests completely ignore.
So let's explore exactly how those hidden vulnerabilities are exploited in Section 4, Side Channel Attacks Explained.
Here is where things get truly mind-bending. Even if your math is flawless, and even if your code has literally zero logical bugs, you are still not safe. Why? Because the computer actually running the math is a physical object sitting in the real world. And side-channel vulnerabilities don't bother attacking the math itself. They target the physical hardware. Think about it like a bank fault. A side-channel attacker isn't standing at the door trying to guess the combination by doing millions of math equations in their head. Instead, they are pressing a stethoscope right up against the metal door. They are listening to the tiny physical clicks. They are measuring the exact time it takes the internal gears to turn, or they are watching the power dial on the wall. In computing, attackers measure running time, power consumption, and use physical fault injection to break what is supposed to be mathematically unbreakable.
Let's actually look at the microscopic clues and invisible attacker targets. First up, timing attacks. If a cryptographic algorithm takes even 1 microsecond longer to process a 1 than it takes to process a 0, an attacker can literally time the computer's processing speed to deduce your highly guarded secret key bit by bit. Next is differential power analysis. Every single time a microchip performs a calculation, it draws a tiny, tiny bit of electricity. Because a processor draws slightly more power to process a 1 than a 0, an attacker can literally hook up monitors, watch the power dial, and track microscopic fluctuations to essentially read your secret key right off the power lines. Finally, we have fault injection. This is where an attacker purposely induces a physical error in the device itself. Maybe they drop the voltage for a millisecond, or raise the temperature, or literally shoot the physical chip with a laser to observe how the output changes when the system panics. This physical disruption can utterly compromise incredibly robust algorithms like AES, extracting the keys without the attacker ever actually touching the math.
Given all of these absolutely terrifying physical and mathematical pitfalls, we finally arrive at Section 5, don't roll your own crypto. You have to trust the standards.
Because the math is so incredibly brittle, because standard testing fundamentally fails to prove security, and because these wild, stethoscope-style side-channel attacks exist, there's a golden rule in computer science to protect against these invisible threats. Step 1. Never ever implement your own cryptographic functions. I don't care if you are a genius-level programmer, you will make a mistake. It's guaranteed. Step 2. Only use standardized, mathematically vetted algorithms. Step 3. Integrate established cryptographic libraries. This is huge. You must let the dedicated teams of cryptographers and security engineers, the people who spend their entire lives updating these specific libraries just to patch the exact physical vulnerabilities we just discussed, handle the implementation. Your job as a developer is simply to plug their securely designed, heavily tested vault directly into your application. Don't build the vault yourself.
So, the crucial point is captured perfectly in this quote straight from our source material. Because of this brittleness, practitioners are strongly advised to use standardized, vetted algorithms and libraries rather than implementing their own cryptographic functions. It is really the ultimate lesson in humility for software developers. The illusion of safety comes from thinking you can outsmart the attackers all by yourself. True safety? That only comes from relying on collective, heavily vetted, standardized systems.
Now, as we wrap up, I want to leave you with this highly provocative thought. Is the device you are watching this on right now currently leaking its secrets through a microscopic change in power consumption? It's entirely possible. Modern cryptography is a brilliant, truly beautiful mathematical achievement, but it resides in fragile physical machines. Understanding that fragility, knowing that the math is only as strong as the physical chip running it, is the first real step to securing our digital world. Thank you so much for joining me on this explainer. Stay curious out there, and I will see you next time.